Hello everyone, I am Dr. Jahnavi Chakravarti, Assistant Professor, Department of Mathematics, Bardhaman College of Engineering. Today in this video, I am going to discuss how to find the numerical solution of first order ODE using Taylor series method. Numerical solution to ODE. First of all, we will consider the first order ordinary differential equation of the form dy by dx is equal to f of x comma y with the initial condition y at x naught is equal to y naught. Sometimes to solve this kind of first order ordinary differential equation analytically it is difficult. So we can use numerical methods to find an accurate approximation of this kind of system. The ODE can be solved using various methods which are categorized as single step method and multiple step method. What is single step method? The method of solving an ODE is known as single step method if it uses the information at one previous point only. What will be multiple step method? Multiple step methods are those methods which use information available at more than one previous points to find the next point. Here we will consider only single step methods. So most common single step methods are Taylor series method, Picard's method, Euler's method, modified Euler's method and Runge-Kutta method. Let us now see how can we solve this ordinary differential equation using Taylor series method. First of all, we will consider the ordinary differential equation. Consider the first order ordinary differential equation dy by dx is equal to f of xy with the initial condition y at x naught is equal to y naught. Let us take this is as equation number 1. Now we will differentiate equation 1 with respect to x successively and substituting x naught and y naught. We get the values. Now look at here what we are doing. This is dy by dx is equal to f of xy. This dy by dx you can write it as first derivative of y dash. Now if you differentiate it again with respect to x, you will get y double dash, y triple dash, fourth power derivative of y, fifth power derivative of y and so on. And if you put values x naught and y naught, then you will be getting second derivative of y naught, third derivative of y naught, fourth derivative of y naught and so on. As this is Taylor series method, now what we will do, therefore the Taylor series expansion of y of x about x equal to x naught is given by yx is equal to y naught plus x minus x naught by 1 factorial first order derivative of y naught plus x minus x naught whole square by 2 factorial second order derivative of y naught plus x minus x naught whole cube by 3 factorial third order derivative of y naught plus so on, which is equation number 2. Now in equation 2, we will put x equal to x1. Putting x equal to x1 in equation 2, we get y of x1 is equal to y naught plus x1 minus x naught by 1 factorial first order derivative of y naught plus x minus x naught whole square by 2 factorial second order derivative of y naught plus x minus x naught whole cube 3 factorial third order derivative of y naught plus so on. So this is the expansion for x equal to x1. This is y1. Similarly, if we put x equal to x2, x3 and so on, we will get y of x2, y of x3 and so on. Similarly, we can find y of x2, y of x3, y of x4 and so on. So this is the Taylor series expansion of y of x. We can change the value of x and we can get Taylor series expansion for different x values. Now let us solve first order ordinary differential equation using Taylor series method. Now let us look at this problem. Here we need to use Taylor series method to solve the equation dy by dx is equal to x square plus y square for x equal to 0.4. An initial condition is given that y is 0 when x is 0. Given dy by dx is equal to x square plus y square. An initial condition is y at x equal to 0 is 0. So here x naught is 0 and y naught is 0. Now this you can write as y dash is equal to x square plus y square. Now let us find y dash at x equal to 0. Y dash at 0 is equal to x naught square plus y naught square. It is 0 square plus 0 square equal to 0. Now in Taylor series method, what we do? We do successive differentiation. Let us take this as equation number 1. Differentiating equation 1 with respect to x successively, we get y double dash is equal to 2x plus 2y y dash, right? From x square we will get 2x and y square 2y y dash. Now let us find y double dash at 0. What we will get? 2 into x naught plus 2 into y naught dash. You can write it directly also. So x naught here is 0 plus 2 into y naught is 0. Y naught dash is also 0. So this is also 0. Now next one we will get y triple dash. Y triple dash will be 2 plus 2 into y double dash plus 2 into y dash into y dash. So this is 2 plus 2y into y double dash plus 2 into y dash whole square. Now if we find y triple dash at 0, we will get 2 plus 2 into y naught dash plus 2 into y naught dash whole square. So this is 2 and these all are 0. Y naught is 0, y naught dash is 0, y naught dash is 0, so whole square will also be 0. 2 plus 0, we will get 2. Now let us put these values in the Taylor series. Therefore, by Taylor's series method, we have yx is equal to y naught plus x minus x naught by 1 factorial y naught dash plus x minus x naught whole square by 2 factorial y naught double dash plus x minus x naught whole cube by 3 factorial y naught triple dash plus so on. Now let us substitute the values. Substituting x naught, y naught dash, y naught double dash, y naught triple dash, we get yx is equal to y naught is 0 plus x minus x naught, that is 0. 1 factorial means 1. Y naught dash is 0 plus x minus 0 whole square by 2. Y naught double dash is also 0 plus x minus 0 whole cube by 3 factorial, that is 6, and y naught triple dash is 2. So what we have got? Yx is equal to x cube by 3. Now we need to put x equal to 0.4. Put x equal to 0.4. We will get, therefore, y 0.4 is 0.4 whole cube by 3 is equal to 0.02133, which is the required answer. Now look at this second problem where we need to use Taylor series method to find the value of y at x equal to 0.1 and 0.2 to 5 decimal places, and the equation is given by dy by dx is equal to x square y minus 1. Initial condition is at x equal to 0, y is 1. Okay, given dy by dx is equal to x square y minus 1, and condition is y0 is 1. That means x naught is 0, y naught is 1. Now this equation can be written as y dash is equal to x square y minus 1. Let us find y dash at 0. We will get x naught square into y naught minus 1. X naught is 0, 0 square, y naught is 1 minus 1, so it will give you minus 1. Now let us take this equation as equation number 1. We will differentiate this equation with respect to x successively, and we will get y double dash, y triple dash, and so on. Differentiating 1 with respect to x successively, we get y double dash is equal to 2xy plus x square y dash. Now let us find y double dash at x equal to 0. We will get 2 into x naught y naught plus x naught square y naught dash. X naught is 0. 2 into 0 into 1 plus x naught square is 0 square y naught dash. Y naught dash is minus 1. So you will get this is as 0. Next we will find y triple dash, which is given by 2x y dash plus 2y plus x square y double dash plus 2x y dash. This one is x square y double dash plus 4x y dash plus 2y. Now let us find y triple dash at 0. What we will get? X naught square y naught double dash plus 4x naught y naught dash plus 2y naught. X naught is 0, so this term will be 0. Plus here also x naught is 0, so this term will also be 0. Plus 2 into y naught. This will be 2 into 1. So we get 2. Next we will find fourth order derivative of y. We will get 2x y double dash plus x square y triple dash plus 4y dash plus 4x y double dash plus 2y dash. This can be written as x square y triple dash plus 6x y double dash plus 6y dash. Now let us find fourth order derivative of y at 0. We will get x naught square y naught triple dash plus 6x naught y naught double dash plus 6 y naught dash. X naught is 0, so it will be 0. Here also x naught is 0, so it will be 0. Plus 6 into y naught dash, 6 into minus 1, so minus 6. Now let us put these values in Taylor series expansion of yx. Therefore, by Taylor's series method we have yx is equal to y naught plus x minus x naught by 1 factorial y naught dash plus x minus x naught whole square by 2 factorial y naught double dash plus x minus x naught whole cube by 3 factorial y naught triple dash plus x minus x naught power 4 by 4 factorial fourth order derivative of y naught plus so on. Now let us substitute the values. Substituting x naught, y naught dash, y naught double dash, y naught triple dash, fourth order derivative of y naught, we get yx is equal to y naught is 1 plus x minus 0 by 1 factorial is 1 and y naught dash is minus 1 plus x minus 0 whole square by 2 factorial y naught double dash is 0 plus x minus 0 whole cube by 3 factorial y naught triple dash, it is 2 plus x minus 0 power 4 by 4 factorial y naught power 4 is minus 6 plus so on. Yx is equal to 1 minus x plus 2x cube by 6 minus 6x4 by 24 plus so on. Therefore, yx is equal to 1 minus x plus 1 by 3 x cube minus 1 by 4 x power 4 plus so on. Now we need to find y value for x equal to 0.1 and 0.2. Put x equal to 0.1 and x equal to 0.2. For x equal to 0.1, we get 1 minus 0.1 plus 1 by 3 0.1 whole cube minus 1 by 4 0.1 power 4 plus so on. If you calculate this value in calculator, you will get 0.90031 up to 5 decimal places. Then if we put 0.2, we will get 1 minus 0.2 plus 1 by 3 0.2 whole cube minus 1 by 4 0.2 power 4 plus so on is equal to 0.80227, which are the required solution. Therefore, the required solution is y at 0.1 is 0.90031 and y at 0.2 is 0.80227. So this is how we need to find the numerical solution of ODE using Taylor series method. Thank you.